Hello, my name is Charlie Barron, and I'm presenting work from our group at the U.S. Naval Research Laboratory to support development of new capabilities for adjusting ocean data assimilation to retain the scales that are resolved by satellite sea surface temperature retrievals. We're seeking to make better use of the high spatial resolution information that's provided by the production centers contributing to GRIST. We work most closely with the U.S. Naval Oceanographic Office in developing the software and evaluating their SST retrievals. We also use the data streams from other GRIST production centers. One of our primary applications for the satellite SST observations is to assimilate the data into forecast ocean and coupled air ocean ice wave models. And in that assimilation, we combine the satellite retrievals with in situ, surface, and subsurface observations. Now, one of the realities in the ocean is that the satellite surface observations outnumber the in situ subsurface observations by about 5 orders of magnitude. If our assimilation capabilities are optimized to make appropriate use of the sparse subsurface observations, that means we're likely not making good use of the dense surface observations. And we want to take better advantage of that detail that's available, particularly in identifying the front and eddy boundaries. So we're presenting work where we're developing a multi-scale assimilation approach as an efficient method to utilize more of the SST data. The present work is focused on regional models, but we anticipate incorporating these applications in our global ESPC or system prediction capability as well. But it's a lot slower to evaluate a large number of experiments in the global models. We're focusing on the regional for the experiment. So what satellite SST data streams are we using? We've got the polar orbiting infrared data from METOP B and C, from the VIIRS on SNPP, NOAA 20, NOAA 21. We're also using the polar orbiting microwave data from the AMSR-2, but this is at 25 or so kilometers coarser resolution. That's coarse compared to the scales we're considering for assimilation. So really the effect of the AMSR-2 is less important for this particular study. The polar orbiters, the IR polar orbiters, give us potentially global coverage at up to 750 meters resolution, maybe 2 times a day, overlap at higher latitude with gaps due to clouds. The AMSR-2 again can fill in some of those gaps with the microwave sensor, but it's coarse relative to the scales here. But we also get maybe 1 to 2 kilometer resolution IR SST from the geostationary constellation, shown here at the bottom left of the poster, every 10 to 16 minutes and extending to maybe 45 to 60 degrees high latitudes. Good coverage from the geostationary at lower latitudes, nothing at the super high latitudes. That's supported by the polar orbiting. We do make aggregate measures of the SST, comparing the SST retrievals from satellites to matchups of in situ data from drifting or mood buoy observations, such that the matchups are within 10 kilometers in 1 hour. We get RMS errors, maybe 0.4 to 0.5 degrees C for our geostationary satellites, maybe 0.3 to 0.4 degrees C globally for the polar orbiting satellites. And these will, global statistics do obscure some of maybe regional variations in our fidelity, but overall it gives us a metric of our skill. We're developing new metrics to compare the SST matchups away from the in situ observations based on overlapping retrievals by polar orbiters. Generally, these are about 81 minutes apart, and have the advantage of giving two looks at the same location of the ocean over different optical paths to the atmosphere. This is shown here kind of in the plot at the middle of the poster. And the the trend would be during daytime pairs of this overlapping, you're going to generally have a warming trend. Globally, we see about 0.09 degrees Celsius warming, nighttime cooling about negative 0.06 Celsius, with about 2 to 4 million matchups in this 3 to 4 day window we're looking at for the comparison. So we're flagging for further evaluation those areas where the deviation in the temperature is far away from these warming or cooling trends. That may indicate unresolved clouds or other atmospheric variations. It may also be related to the movement of a front or some other translation event, but it could also indicate the contaminations. So these extreme warming or cooling events we're flagging. You could potentially do the overlap SST between consecutive geostationary retrievals, but again, that's sampling the same optical path. So there's cloud movement and things like that, but that's not our focus for the evaluation of those metrics right now. So we have an idea of how good the observations are. How do we assimilate that data? We're looking at what's called an observation system simulation experiment, where we set up two cases of the model. This is shown at the middle of the right-hand page. One representing the true ocean, the nature run, one representing an assimilative run that gives us our model forecast, where those two models differ in initial conditions, in boundary conditions, in forcing conditions, such that statistically their differences are similar to what we see in the operational forecast model systems. We can take samples of observations from the nature run, assimilate those into our assimilative forecast run, and then evaluate both of those to say what is the effect on my forecast skill of different approaches. Now, in the top right, you see that in the off the coast of Cape Hatteras in sort of the Gulf Stream region, the detail that's available in the SST observations, the retrievals from the satellites, and then a much coarser representation of points that are super observations at the scale of the Rossby radius of deformation. It's sort of the eddy scale. It's our assimilation correction for the decorrelation scale for corrections in the using the sparse in situ observations, and that level of detail gives us a very good representation of the means averaged at those 20-kilometer scales, but it gives a very coarse correction shown in the third plot compared to the detail in the original data. So to test methods to make better use of that high resolution information, we have a multi-scale approach where instead of assimilating the data once at the Rossby radius scale, we do a first pass at the Rossby radius scale, make a new interim solution, then sample that with relative to different observations to get different innovations of the information, and correct it with half that resolution spatial decorrelation scales, different error covariance model, and make a correction then at a second scale. And you can see the detail shown in the middle of the right-hand column that you get in the multi-scale approach. What we see in the bottom is the comparison of the solution over over this whole domain using the present single scale or the two-scale approach, two-scale, multi-scale approach. And what we see is that we not only get an improvement of the sea surface temperature, but that improvement just from assimilating in the second pass the higher resolution sea surface temperature information gives us an improvement in temperature extending over the upper 100 meters. So we're continuing to evaluate these approaches both in a multi-scale option and also in a developing a new one-step assimilation approach that gives a correction at a continuum of scales that are above a minimum threshold. So this work's continuing, and I thank you for this opportunity to present the results at the GRIST meeting. I would also like to thank the Office of Naval Research for support of this work. Thank you very much, and you can send questions in our online question capability. Thank you. Bye.